you can grow much larger, much more purer semiconductor crystals as compared to what you can do back here on Earth. One challenge of the International Space Station is NASA has very stringent safety standards in place because astronaut lives are involved. So even though this furnace was installed in the space station back in 2011, it was never used for the purpose for which it was intended for, because the experiments never passed those safety tests on the ground before they could be flown to the International Space Station. So that's where we want to come in and say unmanned platforms like ours don't have as much stringent safety standards. So we want to enable those type of semiconductor experiments to be done in space and be brought back.
Hi, wherever you're joining me, I hope you're doing well. Welcome to India Tech Report, a platform dedicated to chronicling and supporting the growth of India's deep tech and climate tech ecosystems, with the occasional segue into other areas of tech entrepreneurship. I'm Hari Arakli, and this is my In Conversation podcast. In this episode, I'm joined by Abhijit, Bhutey, and Vishal Reddy, co-founders of Inbound Aerospace, a startup incubated at IIT Madras. The discussion covers the origins of their journey from an academic collaboration focused on microgravity research to building a company designed for commercial space experimentation. They started simply with how the idea came to Arvind IB, their fellow founder, when, as a PhD student at IIT Madras, he was exploring microgravity through drop tower experiments. The idea became a startup when Arvind was joined by Vishal, whose background includes graduate studies in the US, and Abhijit, a former pilot with the Indian Navy, who aspired to space tech entrepreneurship. In this conversation, they talk about the challenges and opportunities in creating usable microgravity platforms, detailing Inbound Aerospace's mission to develop a reusable spacecraft that will carry research projects to low Earth orbit and bring the experiments back safely to Earth. Abhijit and Vishal also give us insights into microgravity's usefulness in areas including biotech, materials science, and semiconductors, and explain how their vehicle is being designed for efficient re-entry and autonomous landing. The co-founders also share early milestones, including team building, subsystem testing, and initial funding, and reflect on broader trends and gaps in the Indian space tech ecosystem. Captain Abhijit, Vishal, thank you both for making time for this. Been looking forward to this conversation now for a few weeks and really happy that it's coming together. Let's just simply get started with what was sort of the inspiration for all of you to start Inbound Aerospace, and also give us a sort of quick snapshot story of how the founding team came together, and we'll go from there.
Yeah, sure. Thanks, Hari, and thanks for having self and Vishal on board over here. Incidentally, Arvind, who's also very much a main guy as part of the team, he's carrying out some tests back at IIT Madras, and he couldn't join us. So, coming back to your question, so Arvind has been a PhD student of aerospace at IIT Madras, and for the last many years, he was working on a very specific project, which is the microgravity drop tower. It's one of its kind drop towers in the world, with the Chennai one being the fourth largest, and that itself gives only about 2 seconds of microgravity for anyone to perform any experiment, right? And otherwise, there are very few avenues wherein you can produce that kind of an environment. Even the best on Earth is just about 20-25 seconds or so. So the best option is to go to space and be in orbit and get microgravity for multiple applications. So this problem is where it all started, and Arvind thought of creating a platform which can give extensive microgravity. So this was in his thought, and he and Vishal have known each other for a long time. Vishal was doing his masters back in Colombia, and after completing that, when Vishal came back to India, uh, he like quickly took, as fish takes to water, Vishal just joined him. And my story is like I was in the Navy. I was a fighter pilot in the Navy, and always an astronaut aspirant. And somehow the Air Force pilots were more focused. I mean, it was easy for the Air Force pilots to get into the astronaut program, and I had cleared my test pilot exam, but then I didn't get a chance to be part of the astronaut selection. So it was a very conscious call of moving out of the Navy, doing the ship thing, etc. And flying had also stopped after a certain stage in life. So took voluntary retirement and came out with the sole aspiration of getting into space tourism. And that's about 2 years ago when I met Arvind in a space conference in Bangalore. And then we talked about it, and I was talking space tourism, he's talking microgravity research, and that was like the start point for us to collaborate and get together and then work more seriously on this idea. He was just finishing his PhD. I was about to quit my active service, and then from there onwards, it was back and forth. And then Vishal also joined once he came back from the US, and that's how the team got together. And for the last 1.5 years, it's more of drawing board stage. And then ultimately, this year in January, we decided to give it a official form, and that's how we got incorporated and incubated at IIT Madras.
Vishal, you and Arvind knew each other through your research work, is it?
Oh, no, no. There's an interesting story there. So, my mother is a yoga teacher at IIT Madras. She has been teaching here, I think, from about 2015 or 16. Arvind will give you a more specific date. I should be knowing this better. But so, Arvind and other PhD students have been regular yoga students. They've been practicing every week. So, what happened was a bunch of these PhD students were invited home for lunch. And that's when I met Arvind for the first time. So back then, I think 2016, 17, I was in my second year of college. Arvind was the one person using a Nokia non-smartphone in a sea of everybody else using smartphones. So he was the only one using not a dumb phone, but okay, a phone without WhatsApp, without email, without internet capability. So interesting first meet, but yeah, that's where it started.
And between the two of you, what's your recollection of when was the first time that Arvind spoke about creating a microgravity platform in the space and things like that? How long ago was this idea that you remember that you all have discussed?
The first time I heard it, I would say December 2023.
Hmm.
I heard it in May 2023. That's when I met him first. So
Okay.
it's been
Okay.
going on. I think 2021, 22 is when he really thought that he should go in this direction by the time he finishes his PhD.
Okay. Okay.
Yeah.
And from a general audience's perspective, you mentioned something called a drop tower. I mean, from the context of this conversation, I understood it as a device that allows you to literally drop an experimental object, and as it reaches whatever critical level of gravity pull, and it will attain that for a maybe fraction of a second microgravity condition. But maybe you can explain in your sort of technical terms for a layperson what is the use of a drop tower.
So you know that feeling which you get, Hari. Assume that you're trying to press a lift button, an elevator button, and you press it. It's a microsecond for which you feel that sudden weightlessness, right? That is that feeling which we're talking about. Or if we when we get in the cockpit and when we fly, or if it's a turbulent flight, if as a passenger also, you can experience that, but that's for a very brief amount of time. It's actually milliseconds. So, and why microgravity? That we'll come to later, because there are huge benefits which one can accrue in microgravity. So it's important to have that for deep research, or I mean deep experimentation. And the physical thing, you are right. I mean, it's like a 30-meter tower back in Chennai, and it's the fourth largest in the world. So because of the height and the way it's constructed, I mean, you drop something from top, and by the time it touches the bottom, it's about 2.2 seconds, and that's all there is to either study how a flame works or to study a particular reaction happening. So it's like insignificant, right? 2 seconds. So China has the biggest drop tower, and the other options of getting microgravity near the surface of the Earth is in flight. So you imagine taking a big say like a 747 and doing a parabolic kind of a flight, and that's the geometry which will help you get about just 20 seconds of microgravity. That's also far less as compared to being in orbit, wherein it can go up to few months also.
Yeah, so when we say drop tower, and just think of a tall tower in which you're dropping an experiment, and this experiment is inside a capsule. And before the capsule hits the ground, where there's an airbag to break the fall, before this capsule hits the ground, you get to experience that feeling of weightlessness or microgravity, where when the capsule is in free fall. So, I mean, during the course of this conversation, we might be saying microgravity, sometimes we might be saying zero gravity. Some people, when we have our conversations, right? Most people may not have heard the term microgravity, but when we say microgravity, think of the same thing as in zero gravity. It's just the same feeling of weightlessness. But when we talk about the International Space Station, where astronauts are doing research on a regular basis, at that altitude, 350 to 400 kilometers, there's a small amount of gravity. It's never zero. It's on the micro scale, 10 to the power minus 6. That's why we call it microgravity instead of zero gravity. But otherwise, it's the same thing. So we can use the terms interchangeably.
Okay, so before we get into this a little bit more, I'm also curious about the name of your venture. What's the significance of inbound in inbound aerospace?
Yeah, that's interesting.
I mean, Arvind likes to joke. Arvind's last name is IB. He likes to joke that inbound is the full form of IB. But anyway, that's not where it came from. Arvind always has a better answer for that. But inbound is just that we're always bringing something back from space. We're always, whatever you're sending up to space is always coming back, and it's inbound. The spacecraft is inbound. So I guess that's where the name started. But yeah,
So most of the things which go to space remain in space and they just wither away there, or they become debris and come back to Earth in the form of dust. The idea of creating this re-entry vehicle, which we are designing, is to get it back intact. And you need to be on a two-way ticket rather than a one-way ticket. Right? So you're going to space and then doing some stuff there for 3 months, and then coming back. That's how you're inward bound to Earth. So that's why inbound.
Okay, so again, as a layperson, I my basic understanding is that in conditions of microgravity, various behaviors of substances or whatever, even the way plants grow, or maybe medicines crystallize, etc. Some things that I've read is very different from how it happens on Earth, and that probably gives scientists and engineers an opportunity to do more innovative things. But maybe between the two of you, you can give us a sense of, sort of the size and scope of the possibilities that are out there in conditions of microgravity.
yeah, sure. So I think to give you some context on why that environment is beneficial, why the microgravity environment or why the zero gravity environment is beneficial, why did our astronaut go to the International Space Station to grow methi seeds or do those kind of experiments, right? Why couldn't he have done it here back on Earth? So I think there are three important processes. These chemical processes of sedimentation, lack of buoyancy, and lack of convection. So, in the sense, when we talk about sedimentation in an Earth gravity environment or a 1G environment, particles tend to settle down at the bottom of the beaker they are in. That won't happen in a microgravity environment. That won't happen on the space station. And then when you say lack of buoyancy, any particle which is lighter than the liquid that it is in, it tends to float to the top of the surface in an Earth gravity environment. But again, that doesn't happen in a microgravity environment. And then lack of thermal convection, any part of the liquid which is hotter than the rest of liquid tends to rise up to the surface, but then that doesn't happen in a it doesn't happen in a microgravity environment, but happens in a earth gravity environment. So all of these different processes combined, which only happen in the microgravity environment, give rise to certain types of products or experiments that can only be researched in a platform like the International Space Station. Because although you can say that drop towers and parabolic flights offer this type of experiments, this type of environment, for a methi seed to be able to sprout or for it to be able to grow, something like 20 seconds is not enough to see the full range of experiment happening, right? So you need to be able to take it to space and see how it performs. But in terms of the scope of objects, I think even today that we probably don't have the full idea of the products that can be made. I mean, on the one side of things, you talked about protein crystallization and its applications for the pharma industry. When we say protein crystallization, it's the sense that when you try to crystallize these proteins in a earth gravity environment, these crystals reach a certain size, after which they tend to settle to the bottom of the beaker because of their size and mass. This problem is not there in microgravity environment. You can crystallize much larger crystals which don't necessarily settle to the bottom of the beaker that they are in, and this gives benefits in terms of drug discovery, because you can take this larger crystallized proteins, bring it back to earth for further analysis, and these larger protein crystals benefit you from both a drug discovery standpoint and also to see where you can attack a particular it could be like let's say you take a cancer protein to space and then you crystallize it, and then you can see, you can look at the targets better. That is something that you won't be able to do in a earth gravity crystallized crystals, and I'm using the word crystal a lot. But and then one side of things you have the pharmaceutical side of things, and then you also have, in the same pharmaceutical side of things, you have 3D bioprinting. You can, when you try to, you have 3D bioprinting back here on earth. People have done 3D bioprinting of heart tissues and knee meniscus and things like that. But what happens is, in an earth gravity environment, you need to have a complex support structure when you're 3D bioprinting something. So after your bioprinting of that tissue or that organ is done, it's very difficult to remove that support structure or that scaffolding to get what you, the primary object that you printed, 3D bioprinted. But when you go to a microgravity environment of space, that same complex support structure is not needed when you try to 3D bioprint something. So you're able to print these very thin single-celled tissues or organs with great precision without the need of a support structure. So I hope this gives you some idea on the pharmaceutical or biological side of things. And on the other end, you also have the material science side of things, in the sense the International Space Station, they have it has something called a high temperature furnace where you can do semiconductor crystal growth experiments. So why do semiconductor crystal growth experiments into space is because you can grow much larger, much more purer semiconductor crystals as compared to what you can do back here on Earth. And when you take these semiconductor crystals, think of the raw material that eventually becomes the chips in our phones, right? This big crystal ingots that you try to grow in the microgravity environment of space, and then you slice these ingots into wafers, and these wafers eventually our chips are etched onto these wafers. So it has not been done on a commercial scale yet, but the hope is that these wafers will eventually be able to serve higher power electronic applications in the future when we do come to that stage. So, I mean, I've been talking a lot, but one challenge of the International Space Station is NASA has very stringent safety standards in place because astronaut lives are involved. So, even though this furnace was installed in the space station back in 2011, it was never used for the purpose for which it was intended for, because the experiments never passed those safety tests on the ground before they could be flown to the International Space Station. So that's where we want to come in and say unmanned platforms like us don't have as much stringent safety standards. So we want to be enable those type of semiconductor experiments to be done in space and be brought back. But material science and semiconductors are the most lucrative side of things that we want to say we can serve this market, do something commercially and bring it back. But the whole scope, there is an interesting website called Factories in Space. You can revisit it later. We can visit it later when you have time. There they talk about even coffee and whiskey being done in space and then being brought back. So yeah, a lot of interesting things that can be done.
So I think good point now to actually talk about the vehicle that you want to develop or you are developing. Can you talk us through what this will look like? How do you intend to put it in space? And once it's there, how long will it stay? What all can be done on it? And you've said that it's also something that will come back to Earth and be reused. So just walk us through what this is about, this platform's about.
Okay, so let's put it this way. I mean, let's visualize a satellite, and a satellite remains in space, right? And it's not designed to come back. So to get something back from space, it needs to be designed in a particular way. Just using some basic terms, there needs to be a heat shield which protects it from all the excessive thermal heating which is going to happen, and so that it can survive the re-entry once it's coming back to the earth. And for that, we have two options. We could have a capsule kind of a geometry of the space object which is coming back, or it could be in the form of a simple aircraft. But the aircraft is not the most, I would say, uh, optimally suited for the re-entry, and that's why you modify that design and you create a lifting body design, something which is not an aircraft and something which is not as simple as a capsule. So our design falls in this particular category, which is a lifting body design, and it is optimized to come back, negotiating all the distillation loads as well as navigating through the excessive temperatures which are generated. But at the same time, it can also protect the experiments which are being brought back, and the deceleration loads which a body like this has to undergo is far lesser than a normal capsule. So this is like a differentiating factor for our design, which optimizes not only the capsule design but this aircraft design, and that's where we it's like a best place.
Hmm. And to add on to Abhijit's point, to give you like a visual idea so that you can create a mental image, is you can somewhat think of the space shuttle that carried Kalpana Chawla to space. So yeah, perfect. Abhijit has a model of our spacecraft. Yeah. So think of the space shuttle that took Kalpana Chawla to space and brought her back many times, a couple of times, right? Unfortunately, it did not come back the second time. But think of the same form factor, but a much smaller version of it and an unmanned version of that same spacecraft. So the thing about the space shuttle is it had wings, but our spacecraft, Abhijit had mentioned that it is a lifting body. It doesn't have wings. So what he means by a lifting body is that the spacecraft itself is able to generate lift as it glides through the atmosphere without the need for wings. And then on the other side, you have something called a capsule. Our astronaut or all astronauts who go to space today go in something called in those capsule shaped spacecraft, like the SpaceX Dragon capsule or the Russian Soyuz capsule. So the thing with the capsule is you can pack in the most amount of payload. We call it volumetric efficiency. For that volume of capsule, you can pack in the most amount of payload. So the payload is what makes you the money at the end of the day. But and a capsule being the most volumetric efficient on one side of things, and a winged vehicle like the space shuttle being the least volumetric efficient. So we say it is the least volumetric efficient because when you try to pack a winged spacecraft inside a launch vehicle, the wings tend to occupy a lot of the volume and they are kind of wasted volume in the sense you can't pack any payload inside the wings, and they prevent you from packing any other payload because they're occupying so much volume. So we are in between a capsule and a winged spacecraft in the sense we don't have wings and can take full advantage of the launch vehicle that takes us to space. But we, even though we can't carry as much volume as a capsule, we can offer a much more smoother re-entry experience when we're coming back into the Earth's atmosphere. So that kinds of best of both worlds is what we're going for.
Hmm. In very simple terms, how big will this capsule be?
So it again depends upon. Firstly, I wanted to add something from a previous section wherein, the kind of products which can be made in space are not necessarily the ones which we see on Earth, wherein, I mean, we have huge factories running for kilometers long, like the Boeing factory, etc. So, what can happen in space is mostly high value but low volume. So, these are the kind of products which need to be manufactured in space. Now, coming from there and the kind of opportunities which are there as we go ahead in the next decade, it's not that we, as humanity, we want too much of space to manufacture things because they are going to be costly, and the need may not be there as of now, as we see, unless we go into extensive research and extensive niche products which are required. So we've designed our thing so that it can be carried on the smallest satellite launch vehicle from the Indian inventory. It can be bigger than this also, as in when the demand increases, and then probably we can take it on bigger rockets, maybe the PSLV, or we could also go for the SpaceX rockets, etc. But as of now, we've designed it, and the design is in the region of, I would say, 3 meters by 2 meters, so that it can snugly fit inside the payload fairing of the small satellite launch vehicle. That's how the design thesis is as of now. But it can be scaled up as in when the requirement builds up, moving ahead, it can be scaled up.
And typically, how heavy might it be?
So this particular version, we expect, having done the design optimization, we feel that it should be in the region of just shy of 500 kilograms, which is ideal for the small satellite launch vehicle.
So here our only constraint is the launch vehicle. So even if we want to say that we'll go ahead and build a 1 ton or a 2 ton spacecraft, end of the day we are limited by the launch vehicle that is taking up to space. So ISRO's SSLV constrains us in terms of the dimensions of our spacecraft that Abhijit mentioned, 3 meters by 2 meters, but also in the mass of our spacecraft, because SSLV is capable of carrying 500 kg up to a 500 kilometer orbit. So end of the day, that's where our ceiling is in terms of the dimensions as well as the mass.
So that would make it a low Earth orbit, is it?
Low Earth.
And you're developing this to stay up in space for how long? And it will sort of make re-entry on its own, or you guide it from a station on Earth? How does that work?
Yes, so good question. So our max, what we expect is to keep it up there for 3 months, and there is no major limitation for the minimum duration. If there is a very pressing requirement of getting it deorbited within, say, 2 days after orbit, that can also be done. So how this happens is that, assuming that the experiment is required only for 7 days, then we have deorbiting thrusters on board. Incidentally, we ourselves are working on that and trying to do them completely green thrusters, so that they can come back without any hazard, and it also helps in the regulatory clearances. So if after 7 days there's a requirement of getting them back, we deorbit it using, of course, ground stations and communication links, and then it re-enters the atmosphere and then comes back and lands wherever we want it. So it could vary between a few days to 3 months.
Yeah, but the goal is to have it done completely autonomous. So after it enters the Earth's atmosphere, the spacecraft has to figure out on its own how to get to the landing location of our choice.
And in Inbound's case, do you all have a preference in terms of what is the most efficient plus effective way of doing this? Would you like it to land on land, terra firma, or would you like
Yes,
it to
yes,
splash into the oceans and recover it?
Yeah, I mean that's one of our key differentiators, wherein we want to get it back on terra firma, and not only in Indian territory, but wherever. I mean, if the client is from the Australian continent or a Brazilian client, we could deorbit it in such a way that it follows a trajectory and lands back on the runway. So why this? Because it's observed that whenever a capsule lands back in an ocean or in a desert somewhere, huge amount of search and rescue is deployed in terms of ships trying to fetch the experiment. So not only economically speaking, but time-wise also, a lot of effort goes in fetching the experiment. So that's also one of the key differentiators of this, to land it as close as possible to where the researcher or the industry wants it to.
So one thing I was curious about is that, I mean, I'm imagining in my head that given that this is unmanned and autonomous, so even the experiments or the micro manufacturing processes that's going on inside this spacecraft, all of that is also fully automated, right? And
Yes.
there'll be some communication from a Earth station, and you're able to guide some of those, but otherwise it's all autonomous.
Definitely.
Okay.
Yes,
okay.
yes, completely autonomous. Yeah.
Okay, fantastic. So, can you now give us a sense of where you're at in terms of some early milestones since the time that you all formally started the company? What all have you already done?
So when you think of our spacecraft as a whole, right, there are multiple subsystems that need to work together in order for the spacecraft to perform well in orbit and re-enter successfully and land at a location of our choice. So when we say subsystems, we talk about the aerodynamic shape of the spacecraft, we talk about the structure, we talk about the thermal protection system, we talk about the propulsion subsystem, and then we talk about the guidance, navigation, and control system. All of these things have to work perfectly in sync for us to get for a successful mission. So in terms of where we are at, we have teams, full-time teams working on all of these subsystems who started work on all of these subsystems. So what needs to happen is the design, qualification, and testing of individually of each of these subsystems before we go ahead and assemble the entire spacecraft. So right now we're almost finalized the shape of our spacecraft. We've also done a test of our 1 Newton engine. That's where that would be our propulsion subsystem. We're also working on our guidance, navigation, and control algorithm. That's the software side of things. So a bunch of tests are happening at the same time from different teams. So I think I hope that gives you a good indicator of where we're at currently.
Roughly how many people today at Inbound?
I think we are 20, yeah.
And currently your main location is at IIT Madras. That's where
Yes. The IIT
that's
Madras
where
Research Park, and we
research
keep
park.
shifting between the any outdoor testing. We come back inside the campus. Anything else which doesn't require outdoor testing, we go back inside IIT Madras Research Park.
Okay. I know that there are a lot of moving parts and these things can vary. But what's a rough sort of timetable that you all are trying to work towards? I mean, in terms of a first launch of your first tech demonstrator spacecraft.
So for our first tech demonstrator spacecraft or MVP mission, we are looking to do target Q1 of 2028. So quarter one of 2028 is when we want to first demonstrate the ability of our spacecraft to one, survive re-entry, and to autonomously guide itself to a location of our choice. So that's what we're looking at. Yeah.
And you mentioned Australia and Brazil, and so that sort of got me thinking in terms of who might be potential customers and so on. But and so any early potential partnerships that are already in the works?
So it's let's spend some time on how this model works. So I'd like to tell you that we are not solving the launch problem, right? The rocket companies are doing that for us. What we are focusing is the re-entry part, and after having re-entered the atmosphere, the landing part, right? So now in this whole thing, and the researcher is there, or the industry is there, or the university is there, which want to experience this microgravity. So these are the people who are going to, they can approach us directly. That's one way. However, there is someone called as a payload implementation partner, which will design the experiment for the researcher or the industry. And these payload implementation partners are the one who have the heritage of designing these systems, which can take the proteins, or they can take the molecules or the crystals for experimentation, and we provide the environment, and we act as the high-end logistics partner for getting it back. So now the payload implementation partners, they're very few in number across the globe, and we've started talking with a couple of them. They have also shown a lot of interest. And why this interest is coming in, because like we were discussing earlier, the ISS is likely to be drawn down in the coming years. And these implementation partners also want good stable platforms in space in the absence of ISS to do these experiments. So it's going to be like we are there to get the experiment back. The payload implementation partner is there to design the experiment which will carry, and of course the launch vehicle is there to put us in orbit. So it's like this is the business model, and we've started talking to a lot of implementation partners in the European side as well as Australia. That's where we are.
And you said re-entry is one of the important things that you are solving for. Can you, again, in sort of layperson's terms, can you give us a sense of what are the most difficult sort of challenges here? I mean, I know that commercialization influences many of these things, But let's start with the technical side of things. What are the big technical challenges here?
Yeah. So when the spacecraft is in space, when it's in orbit, or even when you think of the International Space Station, so all of these objects are orbiting around the Earth at close to 25,000 kilometers per hour. So when we do deorbit or reduce altitude of our spacecraft and are approaching the re-entry phase, our spacecraft is traveling at those speeds in excess of 20,000 kilometers per hour, and the temperature it will be facing at somewhere around 80 kilometers and up to 65 kilometers altitude. The temperature would go upwards of 1,500 degrees Celsius. So combined, this challenge of traveling at hypersonic speeds and facing temperatures in excess of 1,500 degrees Celsius will place a lot of thermal stress on the external surface of our spacecraft and on the structure as well. So one very big challenge there is outside 1,500 degrees Celsius, but inside the customer wants the temperature to be maintained at room temperature, so maybe 25 degrees Celsius. So big first challenge is to ensure the spacecraft survives. Second challenge is you maintain the environment inside the confines of the spacecraft as well. And even if everything goes well here, you have to ensure that the spacecraft is still able to guide itself and land at a runway of our choice.
And you also mentioned green thrusters. From that, I understood that as the fuel that goes into the thrusters would be sort of non-toxic, not things like hydrazine and all of that. So, is that now advanced enough in India where you can realistically think of having that on your thrusters in your timeline?
Yes, yes, yeah. I mean, in even if you look at the current scenario, even if you don't have inbound in the picture, you already have players like Bellatrix and Manastu, Bellatrix from Bangalore and Manastu from Mumbai, who are already building green thrusters. So it's definitely, if you take our timelines into account, if you say 2028, we definitely have good options both in India and abroad for doing a green thruster based propulsion system. So that should not be an issue, is what we feel. So, yeah.
Hmm. And just to cover this point for the folks who might be interested in it, can you tell us a bit about any early investors, a quick update on your funding?
Yeah, sure, sure. So for our first funding round, which we just closed as of 2 weeks ago, we just closed our $1 million funding round, about 9 crores. So the investors were Special Invest, Piper Serica, and AC Ventures. Very fortunate to have them on board. We think uh, like these are investors who have invested in deep tech in the past, even in space tech. So I don't think there's a very handful of people who've had a ringside seat to what it takes to build a space tech company from scratch in India. So compared to the space companies of before, Agnicool and Skyroot, who started back in 2017 and 18, and maybe even Dhruva Space and Bellatrix, who started even before that, there was no central regulatory body like in space to help coordinate all space activities. There was not as much of a helping hand infrastructure that ISRO or InSpace was providing. So I think they have gone through the struggles, more difficulties than we have had to encounter, at least at this stage. I'm not saying our problem is easy, but it has become that much easier because they have gone to some of the struggles, and we have the benefit of having some of the investors on board who have seen some of those struggles firsthand and understand what it takes to build a successful space tech company. So,
And I'm thinking this $1 million seed money may not get you all the way to your full fledged tech demonstrator, right? You may need to raise another one or two rounds along the way. So those might be happening in parallel already.
So we're looking at next year, somewhere Q3, wherein we would raise a much bigger round, and that would again be dictated by the launch costs at that time, point in time, and whether it's from the Indian rocket companies or the foreign ones, that will really determine what size of round we need. Because in this tech demonstration or this game, the launch costs are the biggest, the biggest chunk of the experiment. So you're right. I mean, this will just help us, design it together and prove certain subsystems, but the actual flight would happen with a much bigger round.
Hmm. And what milestones, if you successfully achieve, will make it easier to get that money?
okay, so one thing is we finalize the critical design review of our spacecraft. So essentially, we say that the shape of the spacecraft has been finalized, and you have finalized where every single component, your screw, nut, and bolt is going to sit inside the spacecraft. So your critical design review kind of locks in every single component, and then you say, "Hey, I'm ready to build out the space qualified version of this spacecraft." So when you say I'm ready to do that, you have qualified all or most of your subsystems, and you know how much exactly everything is going to weigh, or how much volume it's going to occupy, and then you say, okay, design is ready to manufacture, and then take that to the next round.
And what else can we highlight in terms of any innovations that you think will stand out from the point of view of inbound's work? For example, you said the conscious decision to decide on a particular shape for your spacecraft. Is there anything else that comes to your mind, whether it is in terms of materials used? I mean, you already mentioned the green thrusters, and in other ways, because now some of these technologies might have become mature just as you have started building inbound. I mean, I'm just thinking aloud.
So, anything in space, like assuming that this has to stay up there for 3 months, it'll require a lot of power, right? If it's a short sortie, then you can afford to do it with battery backups. But in this case, we'll have the requirement of solar panels, right? So what we are also trying to innovate back at Chennai is to get them develop rollable solar panels. So they actually roll out, stabilize, harness the energy, power up the spacecraft, and when it's time to come back home, they roll in again and snugly get inside the outer structure, and that's how we get it back without leaving any kind of debris behind. So that's one of our major things, and happy to share with you that we've also applied for the Smile platform. Smile platform is the small satellite module experiment in LEO, which will happen next year early, and that's where we've applied for, and we're also working strongly towards that, so that we can get some kind of a miniature design of a rollable solar panel. So that also is like a great thing to work on.
So I want to ask a question that's sort of flip side of what you just earlier said, Vishal, about how now, because of the significant number of steps government has taken in terms of policy making, and over the years making India part of many international treaties and all. And I'm sort of adding this point, building on what you said, which has kind of made it now easier for newer space tech startups. So the flip side is, what is still missing in terms of the broader ecosystem in India for space tech / deep tech companies like yours?
I would say the risk appetite. I mean, it doesn't have to necessarily be for venture capital. I think even from what is preventing the next IIT Madras aerospace graduate who has worked on the student rocketry team to go and build a startup of his own. So is not necessarily the students' risk appetite, is it the students' parents' risk appetite? So where does culture come into play, or where does the government regulation come into play? So where do you say, does the student have enough of an appetite to go and say, hey, let me go and try to build out this startup for the next few years? If I were to put that same student in a US environment, or in that same high school or college environment, maybe you would have had more confidence to go and build out something like that from scratch. I mean, that is just something I'm thinking of from the top of my head, but just observing some of these student teams who are sitting right below us, because a lot of talent that tends to go into industries apart from aerospace, like they might go into some other industry. So that's when you think, okay, there's a lot of talent that could have gone the deep tech side, but is instead choosing to go somewhere else. That might be because, of course, those other industries pay well, pay better as compared to deep tech. But that's something that I'm thinking of. But yeah, we hope to lose some of the talent.
If we go back in the 90s when those economic reforms took place, and we had a kind of an inflection point, and I feel that we are at another inflection point here in terms of the startup reforms, and lots is happening. I mean, you're most welcome to visit IIT Madras and the pre-incubators, the kind of things people are developing. So I think we are heading that way, wherein the entire ecosystem is changing for good, not only the government, but the commercial aspects of things, and the thing of you know, proving to the external world that, I mean, we have the brains here, and just with little support from the governance, etc., we can really make it big. I feel that we're just at the cusp of that. Within 5 years, maybe people would be writing books on us, like Startup Nation written on Israel. So I think we're just there. We're just there.
Yeah.
All right. So one last sort of standard question as we begin to wrap this up. I mean, leading up to 2028 and over the next 1 year, 18 months, what might be your top priorities?
I would say, I mean, Abhijit might have a different answer as well, but for me, I think building out that core team and getting that correct culture in place, I think that really influences how your product building happens over the next, not only till 2028, but over the next 5 or 10 years. So that once you have that culture in place, whatever product you are building, I think that will be really helpful. So I think over the next 18 months, how we grow and expand a team, what kind of talent we're getting into the picture, I think that is really important. The technical challenges, of course, will be challenging. We will find a way to solve them, but the people who we do it with, I think that would make a big difference. So yeah, that's something.
Yeah, absolutely. Bang on. It's more about getting in the right team to solve these challenges. I mean, rather than a big company which has a lot of procedures in place and SOPs in place, it's this is going to be our biggest endeavor right now.
That's it for today. You can find links to Inbound's website and the founders' bios in the show notes, wherever you get your podcasts. For my pick of daily headlines on deep tech and climate tech from India and around the world, please listen to my India Tech Report Daily Morning Brief podcast. To support my work, please subscribe to my free newsletter, India Tech Report, if you'd like to get all these in one place. I'm Hari Arakli. Thank you for listening.